Thank you.
So this is a piece of work that stems from a number of trips that John and I have run with students and for students, training courses and research trips to the island of Milos in the Aegean, and I'm going to draw some broader conclusions about mass wasting, so landform modifying events, debris avalanches, landslides, etc., and what role they might have to play in the formation and preservation of submarine ore deposits. So the seafloor topography is a very dynamic environment and a very rugged environment, particularly when we get to arc environments. I'll show you some bathymetric images in a second, but it wouldn't be very surprising for us if we were to take an ROV underwater to see landforms like this at the bottom of the seafloor. Some of the scale of some of the images we've seen this morning, we've been a little bit closer to features like this, and we've seen the little crabs scuttling for their precious lives. But these landforms give us a very rugged topography, which is potentially quite unstable and subject to mass wasting events. So the questions I'm going to ask and hopefully answer in this talk are: what are the impacts of those landform modifying events on the hydrothermal systems, and does it give us any differences between on and offshore mineralization processes and the final deposits that we can see in the geological record? Most of this work has been published this year in an Ore Geology Reviews article. So I'll touch on this very briefly. Manuel's already given you a really nice introduction to seafloor massive sulfide systems. So seafloor massive sulfide systems in arcs may include a magmatic source of volatiles rather than just a heat engine at depth driving circulation of originally marine water. So there might be a stronger component of metals introduced from that volatile source. And in terms of precipitation mechanisms of the metals and the minerals, so the ore minerals and the gangue minerals, our main mechanisms in these systems include cooling with or without mixing and boiling in systems that are sufficiently shallow that pressures will allow boiling to occur. So we're looking at deposits in arc environments that are probably less than 1,000 meters where this process is relevant. And here we've got a cartoon cross-section. This is Brothers Seamount from de Ron's article, and you can see he's got a classic stratovolcano cone with a resurgent type dome, steep-sided in the middle. It's a very steep topography, just to show that in bathymetry. So this is Colombo, which is a submarine volcanic edifice associated with Santorini in the Aegean Arc, and we're going to take you elsewhere in the Aegean Arc in a few slides. Colombo, actually, in its crater in that central depression, hosts some actively forming massive sulfide mineralization, but you can see, there's a really strong topographic gradient. So we're going from subaerial exposed in this grey shaded area to 1,600 meters depth. So a very rugged topography. And this is Brothers, so this is a different version of a figure that Manuel's already shown. So there's over 11 kilometers of relief in cross-section across the arc. And when we look at Brothers Seamount in particular, we're looking at something on the order of hundreds of meters up to a kilometer of relief within that single volcanic edifice. These are steep, not particularly stable environments, and as volcanic arcs, they are subject to seismic events and volcanic events, which can further contribute to landform modifying events. So we're going to look at a small site. So this was worked at the turn of the 20th century, in particular for lead, silver, and zinc. This is the island of Milos in the Aegean, so we're a couple of islands away from the Santorini and Colombo, which I just showed you, and we're going to look at Triades here. Okay, so the landform at Triades, again, we're on quite a steep topography. Our interpretation of the topography is that what we see now is not particularly modified from what it would have looked like when it was submerged. We've got a series of lava domes in the rear of the picture, and in the foreground we've got a pyroclastic or a clastic apron derived from that material, which is interspersed by these domes or mounds of material which are hydrothermally altered and hydrothermally cemented. And these are the steep-sided domes, and when we look at them in detail, there are clasts of altered breccia, variably barytized and silicified. We can see some partially altered dacite in there, derived from that dome material. We can see reworked pieces or clasts of hydrothermal material, including clasts composed of lots of barite and quartz. So we're seeing our submarine gangue mineralization, and at the base of some of these structures, largely worked out, this has been historically mined, there are very occasional pods and pseudo-vein-like structures which are composed predominantly of sulfides with some chalcedony, quartz and barite mixed in there. And that's what these, back at the turn of the 20th century, people would have been pursuing here. They were mining out these pods for the lead and zinc and silver content in particular. When we look in some detail at that, so we wanted to reconstruct the paragenesis. This was work done by student Sam Bicknell at the University of Leicester as part of his MJOL. He reconstructed the paragenesis of this deposit. It's been variably described in the literature as different kinds of systems, high sulfidation epithermal, which it absolutely is not, and a Kuroko type deposit, which it also is not. So, you know, Sam can't do anything wrong, really, can he? Because everyone else has got there first. And what we see is a fairly basic sequence of minerals. There's barite and quartz throughout, and really the beginning and the end of the deposit is always marked by this big period of barite and quartz formation, and then relatively restricted range of sulfide minerals, pyrite, galena, sphalerite are the main ones, and a little bit of tennantite, tetrahedrite, very tiny amounts of chalcopyrite. This system is probably not hot enough to precipitate or to carry chalcopyrite around in it. And very frequently when we look through some of these vein systems, we see the sulfide mineralization interrupted by periods of no sulfide, just chalcedony, later on recrystallized to other silica phases. So it's not very continuous mineralization. It's a relatively underwhelming deposit. I'll just put it out there, but it's a very nice place to do field work. Which there's a few people in this room who've been with us who will not argue. So if you question us on doing field work in Milos, you don't get to come on the trip. So there's very little gold in this system and very little copper. Okay, so another one of my students, Helen Bennett, worked on the fluid inclusions. So we get some that have got a spuriously high temperature. That's because we looked at fluid inclusions in the barite phases too, and they're very subject to post-entrapment modification, particularly stretching and necking. So ignore the ones at the high temperature. What we see typically is this array around 200 degrees, and we've got good petrographic evidence, as well as this vertical array indicates that this was a boiling or a boiled system. So somewhere in the subsea floor environment, there was boiling happening in the system. And that in part explains the absence of chalcopyrite in this system. Chalcopyrite would probably be precipitating at temperatures well in excess of 200 degrees C. And the boiling is essentially capping the temperature of this system to 200. This little low salinity cluster down here are probably the vapors or the steam that's been recondensed and trapped in little quartz crystals. So condensed vapors down there. So we put together the mineralization or the mineral paragenesis, we put together the field relations, we put together our fluid inclusion story, and our sort of cartoon-like model for this system is that we've got a series of lava domes in the area, and on the periphery and margin of these we have the expulsion of fluids which are boiled somewhere in the subsurface. The dome itself is prone to mass wasting events. There are lots of debris flows or block and ash flow type deposits in the vicinity of this area, and the breccia mounds that are constructed out of the barite and quartz and the re-cemented silicate clasts are also prone to collapse. They form very steep-sided domes that are probably above their own angle of repose. And these periodically are either wiped out by other landforming modifying events or collapse under their own weight and are reworked continually. When we have those landform modifying events, we have incursions of cooler seawater, we interrupt sulfide mineralization and precipitate zones of chalcedony instead. So what we're seeing here is that mass wasting at Triades is interrupting mineralization, and it's essentially truncating the ore bodies. Mass wasting in this environment has not been positive to this ore deposit. Now, when we go onshore and we start to talk about mass wasting, in onshore deposits, the equivalent of the system, something that boils in the subsurface, quite often mass wasting events can actually, and perhaps not quite logically, but they can actually have a positive impact on mineralization through a process known as telescoping. So I'm hastily drawn cartoons, the power of Microsoft Paint. In an epithermal type environment in a volcanic arc edifice, we would have some sort of reservoir of fluid which may be capable of producing mineralization, and it would do that at some temperature and pressure, or temperature and depth condition, which it is capable of boiling. And when it boils, it precipitates the minerals that we're interested in, typically gold in this environment. If we have a mass wasting event which removes part of that volcanic edifice, our pressure re-equilibrates, our gradient, our depth is re-equilibrated, so we shift the boiling zone down, and we could end up superimposing boiling zones above each other and increasing grade appropriately. In very extreme examples like the Ladalam deposit in Lihir Island, epithermal gold mineralization has been superimposed over much deeper porphyry-style mineralization. It can sometimes be a significant boost to the grade and tonnage of a deposit by superimposing zones of mineralization above each other in a very short space of time, essentially catastrophic ore precipitation. In a submarine system, that doesn't really work because our main precipitation mechanisms are at that discharge interface. These are largely exhalative features with some degree of replacement in that near shallow subsea floor interface. Our boiling zone might be significantly decoupled from that zone of precipitation and discharge. And the effect of mass wasting is simply to remove that ore body and start a new one on the new land surface. Our boiling zone doesn't shift significantly because it's actually controlled, rather than depth below surface, depth below sea level. That is our controller on our pressure. So there is very little scope for the telescoping of submarine ore deposits, and mass wasting instead literally truncates the deposits and removes the exhalative portions of them. In some cases, we might actually be able to trap these and retain them if we're in a crater-type environment. So Eskay Creek, for example, is a very large gold-rich deposit, and most of it is hosted in breccias, which are probably derived from the collapse of domes during mass wasting events. But in short, seafloor massive sulfide deposits are not really enabled or facilitated by mass wasting events. Instead, probably what we see in the geological record preserved onshore is that we misrecognize a number of submarine systems, and instead what we see are epithermal systems. So there are gold-rich epithermal veins at Prophetys-Ilias, which have some meteoric water component, but also a significant marine water component. So we're probably misrecognizing some epithermal deposits, assuming they're terrestrial, and actually they are submarine boiling systems. At Milos, Prophetys-Ilias tracks that transition from submarine to subaerial. So the final slide, the implications are that mass wasting and landform change is very likely in arc environments. They're topographically complex areas with volcanism and seismicity, but that gives our deposits very poor preservation potential. They are near-surface deposits. Mass wasting limits the size of the deposit and has no positive effects on them, and our well-exposed areas, the ones prone to mass wasting events, prone to denudation, are the ones most likely to be exposed at the surface. They're also likely to be some of the smallest deposits. Our best deposits are likely to be in areas that have a high preservation potential and are continually buried. If you are Nautilus, that's not good news because it means your deposits are buried. So very challenging to explore and to mine. Okay, thank you very much.
Thank you very much. One quick question if we have anybody. Questions for Daniel? Okay, thank you, Daniel.
Dan, I'll ask you one then. So if you are in a mass wasting environment, though, presumably boiling and subsurface deposition is preferential over exhalative activity because the chances of preserving mineralization at depth are higher than anything formed on the surface.
Yeah, but the lack of telescoping potential in that system means that they're probably very underwhelming epithermal type veins rather than being significant. From an onshore perspective, I think it would be very hard to tell the difference. You'd be looking in detail at the salinity of the deposits. So, you know, a prophytosilias type model, you might see much higher than expected salinities in the epithermal system. If you are a company like Nautilus pursuing seafloor deposits, then a mass wasting environment just means you're looking at small deposits, basically. There's no real benefit to them, unless you can intercept the material that's been transported off, because that might be accumulating in some sort of basin. But I suspect that would be very difficult to explore for, because you lose in those geophysical signals that we've heard some of the speakers talk about this morning that give you massive sulfide accumulation.
Interesting, but that's exactly what we have in the Atlantic ridge, these basins.
Yeah. Well, and Colombo's crater hosted as well. So if there is, you know, a vent collapses, it basically collapses into its own structure. But when we get to arc environments, you know, Pacmanus Basin, Kermadec Arc, we're potentially just shedding off the ore deposits. So, which makes them a very challenging exploration target.